Alright, welcome back to section 6.3, Vectors in the Plane. This video will cover examples 8 and 10 in your notes. Here you'll be learning how to find the direction angle of vectors and use vectors to model and solve real-life problems. So let's go and get started together. Alright, example 8, we're asked to find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizontal. So in the diagram, 30 degrees is this angle between the negative x-axis and the terminal side of the vector. So with component form, let's call it vector v, is equal to the magnitude of this vector times the vector itself. So cosine of the theta times sine of the theta. Well, because the reference angle is 30 degrees, from the positive x-axis all the way to the terminal side, it's really 30 degrees plus 180. So this theta is actually 210 degrees. So plugging in numbers, the magnitude, of course, is the speed of the airplane, so 100. So now I've got cosine of 210 degrees, sine of 210 degrees. Now, using the reference angle of 30 degrees, I know that cosine of 30 degrees is root 3 on 2, and the sine of 30 degrees is 1/2. So down here in quadrant 3, these two coordinates must be negative root 3 on 2, comma, negative 1/2. So swapping out these values, 100, cosine of 210 is negative root 3 on 2, and sine of 210 degrees is negative 1/2. Let's go ahead and distribute this 100 through. So put this over 1 for a moment. So I have negative 100 root 3 all over 2 inside my vector. Let's see, 1/2 of 100 is 50. So negative 50. Simplifying here, divide by 2, get 1, divide by 2, get 50. So the final component form of this vector must be negative 50 root 3, comma, negative 50. All right, go ahead and box that answer. All right, go ahead and try exercise 97 in your notes now. Make sure you do draw a triangle so you can find the cosine and sine of 30 degrees. Check your answer in the back of the book. Come back when you're done. All right, before we look at example 10 together, it's helpful to remind ourselves that until this point in our studies, we've always measured degrees starting at the positive x-axis. So for example, this is 45 degrees, or going all the way around, this is, for example, 330 degrees. That's not always the case, and this next example is going to show us that. When we're talking about air navigation, we actually use something called bearings. And bearings are measured in degrees clockwise from north. So if we instead take a coordinate plane and label it as a compass, so never eat soggy worms, we start at north and measure clockwise. So this would be 45 degrees. When we use calculations, though, using the unit circle, we would say that this 45 degrees would be the same as 45 degrees from the positive x-axis. So if a plane has bearings of 330 degrees, we again start at north and go around 330 degrees. But unit circle-wise, well, I know this has to be 30 degrees, so this angle would be really 120 degrees. And we would use 120 in all ensuing calculations. So let's take a look at this together in an example. So it says an airplane is traveling with a speed of 500 miles per hour. So think the magnitude of this vector. It's got a bearing of 330 degrees, which we can see from north all the way around is 330 degrees. So unit circle-wise, because this is 30 degrees sandwiched between here, this must be 120 degrees. So as the airplane reaches a certain point and encounters a wind blowing with a velocity So a second magnitude of 70 miles per hour in the direction 45 degrees east of north. So if I were just to draw this vector, starting at the origin, it would look something like this. So here's the 45 degrees it's bearing, but unit circle-wise, we're more interested for calculations in this 45 degrees as it's measured from the positive x-axis. So the question is, what's the resultant speed and what's the direction of the airplane? So we can actually use vector addition to answer this question. So if we take this green vector representing the wind and simply move it to the plane's position and connect where we start to where we finish, this red vector is the resulting speed and direction of the airplane. So this is v1 plus v2. Now we actually have all the tools we need in order to find this. So let's break this down and get each vector into component form. So vector 1 is the plane. Its magnitude is 500. We've got cosine of 120 degrees, sine of 120 degrees. Let's swap out those values inside the vectors with unit circle values. So cosine of 120 degrees is negative root 3 on 2, and sine of 120 degrees is 1/2. Let's multiply these in. So I get negative 500 root 3 all over 2. A half of 500 is 250. I see I can reduce this fraction, divide by 2, and get 250. So vector 1 can be rewritten as negative 250 root 3, comma 250. So we'll highlight that because we'll come back and use that in a minute. Vector 2, the wind, its magnitude is 70, cosine of 45 degrees, sine of 45 degrees. Swap those values out. Well, cosine of 45 degrees is root 2 on 2, and sine of 45 degrees is root 2 on 2. Distribute this 70 in and get 35 root 2 and 35 root 2. So here's vector 2. Let's highlight that too. So really, we're looking for what's this resultant vector. So if we add these, I can say vector 1 plus vector 2 is equal to, let's add the horizontal components, negative 250 root 3 plus 35 root 2, comma 250 plus 35 root 2. Grabbing your calculator, we can say that this vector comes out to approximately negative 200.5, comma 482.5. So remember, this is in component form. And that's great. So to actually answer the question of what's the resultant speed and direction, because it's in component form, I can say the magnitude of vector 1 plus vector 2 is equal to the square root of its horizontal component squared plus its vertical component squared. Grabbing your calculator, you find that comes out to approximately 522.5 miles per hour. Go ahead and box that answer. So one question down, we found the speed, but now we need to find the resultant direction. So we can use tangent of this theta is equal to the vertical component all over the horizontal. So tangent of theta, let's see, my vertical component was 42.5, and my horizontal is the negative 200.5. So plug in numbers. Now taking the inverse tan, so swap the arguments. So 42.5 all over negative 200.5. We get theta. So grab your calculator, make sure you're in degree mode. Let's take the inverse tan of 482.5 and divide by negative 200.5. enter. Well, I get theta being approximately negative 67.4 degrees. Well, again, that's measured from the positive x-axis. So negative 67.4 degrees is down here. But looking at a resultant vector, negative 67.4 degrees is not a logical conclusion. We need theta to be in quadrant 2. So in order to rectify this, we take this negative 67.4 and extend it into quadrant 2 by adding 180 degrees. So theta comes out to approximately 112.6 degrees. Whew. All right, go ahead and try exercise 105 in your notes now. So it says an airplane is flying in the direction of 148 degrees. So they're talking from north. So all the way down the airplane, bottom vector is 148 degrees, which going from the positive x-axis all the way around is 302 degrees. Let's see, because the wind is this tiny vector here, its ground speed and direction as a result are 800 kilometers per hour and 140 degrees. So that's the second vector here. So because of the wind, the plane is now flying at 140 degrees, which comes out to 310 degrees. So I can say the resultant vector is equal to my original vector, what the plane is set to, plus wind. My hint to you is to get the resultant vector using 310 as a linear combination in terms of I and j. Do the same thing with the original vector. If you then subtract the original from the resultant, you'll find the wind. Check your answer in the back of the book. Come back when you're done. All right, go ahead and try the wrap up for examples 8 and 10 in your notes now. So number 1, you're asked to find the component form of the vector. I see the magnitude of this vector is 100, and it's an angle of 45 degrees below the horizon. So if that's 45 degrees, think really carefully about choosing the appropriate theta. And number 2, an airplane is traveling at a speed of 724 kilometers, so there's your magnitude, at a bearing of 30 degrees. So that's 30 degrees here. As far as the unit circle calculations, that's 60 degrees. And the wind velocity is 32 kilometers, so a second magnitude. It's blowing from the west, so the wind is actually headed to the east. So it might be helpful to get that in there. Let's see, 32 kilometers from the west. So it's pointed to the east. Go ahead and find the resultant vector. It may be helpful to move that resultant vector tip to tail, and then connect the dots from where you start to where you finish. All right, come tomorrow with questions. I'll see you soon.